Hello and welcome back to another lecture from organic chemistry. So we started the NMR discussion, and we said that we have a nucleus, that it has a magnetic field, and the magnetic field of the nucleus, it can have interaction with the radiation that we are applying. And based on like interaction we get with between those two, we can identify the unknown sample or get us an idea about structure of the sample. And then any NMR that you pick, you will see that like there is a superconducting magnet, called that when you pass electricity through it, it depends what's the current, you will get a magnetic field there. And now, when do we get superconductivity? We get it when the temperature is really low. And then in case of NMR, we drop the temperature to almost 4 Kelvin. And in order to go to that low temperature, 4 Kelvin, we use helium, liquid helium, to cool it, and also to save money and stop helium from getting evaporated. We cover or surround the helium by liquid nitrogen. So the inner one, it has helium, liquid helium, and that one, like outside of it, is surrounded by liquid nitrogen. And where is the sample? As you see, the sample is in the middle, and you can say that's actually the temperature there. It can be around the room temperature. Why? Because it's open, open to the air, and we can we have the right we have the technique to play with the temperature, bring it down, up, and see the type of interaction we get in different temperatures. Okay, so what do we get from an NMR spectrum? We get 4 inputs. The first one, it says number of signals. So this one is going to give us number of non-identical hydrogen or protons. Okay, so if I see 4 signals, that means I have 4 different hydrogen atoms. Next one is the signal location, and that's or the chemical shift. We show it by gamma, and I'm talking about this. Okay, the position. Okay, where the or location of the signal, it will give you a good idea about the electronegativity that hydrogen atom is dealing with, or that element is dealing with. Next one is the intensity, signal intensity. Signal intensity, it will give you, or the integration, it will give you idea about number of identical hydrogen atoms. And it says integration. Usually they show it by this kind of like this sign, or also you might see some some number written at the top of the peak, or the signal, or at the bottom of it. So for this case, you might see 2H here, or round 4 is going to say 2H. That means that signal represents 2 hydrogen atoms. In case of A, it's going to be 3H. That means 3 hydrogen. And C, it will be, again, 3 hydrogens. So the ratio is going to be 2 hydrogens versus 3 hydrogen versus 3 hydrogens. And if you look to the peaks, you can see some tiny also splitting, or some small peaks there. And that one we call it the signal shape, or the splitting pattern. The splitting pattern is going to tell you technically the type of atom that hydrogen is attached to it, or it will find where hydrogen is located. Okay, so we're not talking about the chemical shift only this time. We're talking about which carbon, for example, atom that hydrogen is attached to it. And so, for example, in this, like if I pick one of them, if I go after this one, I see peak got split to 3 peaks, and that's going to tell me that I have a hydrogen atom that is neighbor atom. It has 2 hydrogen atom attached to it. So the peak that I see around 1, we're talking about this peak, is a split, and it's split to 3 small peaks. And this one is telling me that I have a CH. Okay, which H? 1, 2, 3, and it says the 3 hydrogen. So we're talking about CH3. That is attached to a neighbor atom, carbon, that it has 2 hydrogen atoms attached to it. So the splitting or the shape of the peak will give you idea about your neighbor technically. And through that one, we can get the way atoms are attached to each other. Okay, so now let's go after this 4 items: number of signals, location, and intensity integration, and the shape of the signal. The first one is going to be number of signals. If the hydrogen atoms are chemically equivalent, they will give you one signal. Okay, if not, they will give you a different signal. So different hydrogen with that hydrogen atoms that are chemically not identical will give you different peaks. But what will happen if they are chemically equivalent? They will give you one peak. Okay. Now, if the hydrogen atoms are chemically equivalent, not only they will give you one peak, that you can categorize them in two classes. One, homotopics, and the second, enantiotopics. What's the difference between homotopics and enantiotopics? Homotopics, you're talking about hydrogen atoms that they are sitting on a carbon atom, or any atom that we're talking about it, that it doesn't have a chiral center. So there is no chiral center, one. Okay. Also, those two hydrogen atoms, you can transfer, you can technically interchange them, or you can transfer them to each other by simply rotation. Let's call this one A and call this one B. If I rotate a molecule, okay, let's say 180 degree, I can turn HA to HB. So if our molecule has axis of rotation, okay, those two hydrogen atoms, they will be homotopic. Or, okay, how about this? Say the atom that we were talking about, the one that's carrying the hydrogen atoms, the two hydrogen atoms, is it chiral? If it's not, okay, if you change one of this hydrogen to, let's say, D, and it still is not going to give you a chiral center, then you're talking about homotopic. Okay, another way, for example, we have a CH2, there's a double bond there. If I replace, one of the hydrogen to, let's say, hydrogen A to D, next time hydrogen B to D, then like a deuterium, I get those two structures, 1, 2, and can I turn 1 to 2? Yes, we can easily rotate the molecule in this direction. Just flip the molecule. If you flip the molecule, 1, it will be equal to 2. And because they are identical, and in that case, I'm going to say those two hydrogen HA and then HB are homotopics. Now, we said if the two hydrogens are chemically equivalent, they can be homotopics or enantiotopics. How about the enantiotopic? Enantiotopic are the hydrogen atom that if you change one of them to an isotope or any other atom, you will get enantiomer. Okay, so technically you will get a chiral center. Okay, this is the atom this is the carbon atom we're talking about it right now, because we are dealing with two identical hydrogens. There is no chiral center. Okay, but if you change one of them to deuterium, then you will get a chiral center, and it depends where you put that deuterium. You might get R or S. Okay, that's one. Second trick is, instead of axis of rotation, if you can find plane symmetry, okay, if you can turn HA and HB through a plane. So this time I'm going to put the plane somewhere, let's say the plane, we're going to put it somewhere here. Okay, and that mirror, it can mirror A to B. And in that case, we say we are dealing with enantiotopic, like in the hydrogen atoms. Okay, how about the diastereomers? Okay, when do we get diastereomers? Okay, I believe I have some note for you. Okay. Now, I have two isomers. Okay, let's call this one 1, and that one is 2. Only difference between them is position of the iodide. And in one case, iodide is across from bromide. The second side is the same side with bromide. We call this one trans. And the second one, we call it cis. Now, these two, they have the same formula. Okay, the only difference between them, position of iodide in the space is different. What's the relationship between them? If you're dealing with two isomers, that the only difference between them is one is cis and the second one trans, we say these two are diastereomer. Okay, diastereomers. That's one case. So cis and trans always will be diastereomer. Another way to have diastereomer, if you are dealing with two chiral center. So one chiral center is here, and that's the second chiral center. The first one is R. The second one, it has a S configuration. So I said the first one R, the second one, it will be S configuration. Now, what's the relationship between this structure and the second structure? Now, check the first carbon. The first carbon stayed as it is. It did not change. But the second one, we flipped it. Okay, from S, we turned it to R. If half of the molecule got flipped, in that case, we say you are dealing with diastereomers. So the second molecule, it has one R, but now we got here we got 2R. Okay, so these two are identical. These two are identical. The difference between them is here. If one of this, only one of the the chiral center get mirrored in the second state as it is, in that case, you're dealing with again diastereomer. Okay, let's go back. Okay, now I have a molecule that's the top carbon is it has R configuration. The next one, this carbon, it has two hydrogens because they're identical, so it's not chiral. Now, if I replace one of them by, let's say, deuterium, then I will get I can have R or S configuration. In this case, we're going to get this one could be carbon number 1, the first priority. This is the second priority, and that one the third one. So I go 1, 2, 3 clockwise, and because this hydrogen is facing to us, I need to flip it, so it will be S. So this one it will be S. That means this one is going to be R. So what did I get? I got R and S configuration. Well, here is R and R. One of the chiral center got flipped, while the second one stayed as it is. Okay, in this case, the first group stayed as it is. So those two are diastereomer. Okay, you can use this technique to find whether you are dealing with homotopic, non-geotopic, or diastereotopic hydrogen. In this case, because these two hydrogen will give me diastereomer, so I'm going to call them diastereotopic. And this is going to be the end of this lecture. And thank you very much.